Yes, good day. This is Aloysius Bamdagalba. I'm presenting a computer model fusion performance evaluation after compression in tiny machine learning applications at the edge. We're considering computer vision, model compression, model performance, and tiny machine learning. My supervisor is Mr. Galangamobi. So before we get into it, now machine learning models are normally deployed on small devices or edge devices. Let's say watches, microcontrollers in cars. When you look at the Tesla that tries to do autonomous driving, but now all these are fast processes that require very fast output from the model so that it can inform probably the processes that follow. But this can't be done when models are compressed and when they have to trade off either the performance for the model size in terms of maybe inference, let's say accuracy or loss or specificity or precision. So we can't probably move in that direction. Yeah, so our introduction here, the deployment of deep learning models on tiny machine learning devices often involves compression techniques such as quantization, pruning, length distillation, which can lead to decline in model performance. Yeah, so CNH impulse model demonstrated this clear advantage for low power, resource constrained environments requiring only 4.5 kgb for random access memory. However, this came at a cost of lower classification performance. Yeah, so there is that trade-off, probably. Lower classification, lower accuracy or precision, or lower inference, more time, more time required for an output to be given. But now, the study aims to address the performance decline in tiny machine learning models and propose strategies to retain model accuracy while optimizing computation efficiency. Continue. Related work. What have people done? Tiny models were trained by Keaton and colleagues using a similar kind of training from Caruana, who was also a researcher who did some work back then in 2006 on knowledge distillation with ensemble models. So I was using ensemble models to train smaller models, which kind of had experiments and also results, which I used to probably inform my work. But me mainly I used vision transformers because they're the new CNN plus self-attention hybrid models that are being used for work in terms of computer vision currently. They have the best performance around it. Yeah, we just need a large data set to probably cut their performance. So, yeah, in this distillation process, there's a transfer of knowledge from a heavy model to a tiny model that is more suitable for deployment on an edge device. Caruana and his colleagues demonstrated that the knowledge acquired by the large ensemble models was transferred to a single small model. When distilling the knowledge from the large model to a small one, however, we can train a small model to generalize in the same way as a large model. One of the most daunting challenges in model compression is the trade-off between its size and performance. The compression algorithms involve information loss that can hurt the performance of the model, especially pruning and quantization, which involve removal of weights. Yes, so problem statement. Deployment of computer vision models on edge devices require reasonably low inference and a model that can fit their computer power constraints. Now, these edge machine learning model applications either trade size for inference or the other way around, which creates a void that needs to be filled. Now, research questions. To what extent does compression in model size impact on inference time on edge devices? What's the best method of compression that balances both model size and inference time? And what model performs best of inference and model size to compression? Research contributions. I deduced Phofonix is the most optimized model for tiny machine learning deployment at the edge due to its low inference time and low size on number of parameters compared to the rest of the full models applied as a student during the knowledge distillation process, because I use the VIT, which learns best better than the transformers and also easier to teach on lesser computation than the ensemble models. Now, model compression. We are looking at the methodology now. How did we do it? Now, the techniques available vary from pruning, knowledge distillation, quantization, to Lorentz factorization. In this work, I applied knowledge distillation using the vision transformer as the teacher model. Why knowledge distillation? Because there was a limited time. I had to go for a low-hanging fruit, which is the best. According to literature that I passed through, I found that knowledge distillation does better um, retention of performance than the pruning and the ensembles, but that's now still a fallacy. I have to prove it so it can become a what? A research proven statement. Yeah, so I just sharpen it and then compare to the rest of the models, distillation process. Then after that, during so now knowledge distillation, then vision transformer. I chose it because it requires less compute. I didn't have compute such as the GPUs, so it uses less compute. But then it also has a higher performance, a learning performance. So I also find models, streaming models for comparison, so they can compare among them and see which one is best to deploy. So the one that is best to deploy is the best available solution. So we first get the best available solution, then after we can see why it's the best available solution, and we know how to probably optimize more on the performance or come up with better techniques for compression. The 5 student models included AlexNet, ResNet, ShuffleNet, VGG, and the famous MobileNet. Now, the goal is to propose a new approach to tiny machine learning model creation that retains all weights in the neural network while minimizing performance loss. Yeah, so weights are not retained in the pruning and also the quantization, weights chopped. But then in knowledge distillation, it's just the calculation or the optimization for the knowledge distillation loss, whereby the comparison has to happen between the student and the teacher. Then the back propagation happens to probably change the weights that are already available, maybe in the small models that you can change, and then come back and predict better on the available data set. So both of them are trained on the data set, and then they come up with predictions. Now those predictions are compared, and then we come up with the distillation loss. Now that loss is always compared for each validation. Now that loss, we captured it in our metrics also. Now, the goal is to propose a new approach, tiny machine learning model creation that retains all its neural network while minimizing performance loss. Now here down, we are seeing our knowledge distillation loss equation, which is equal to the weight decay, which is the alpha, multiplied by the cross entropy loss, which has inputs like the Y true labels and then the student prediction. The student prediction is used twice here, also calculating the distillation loss. There's hard and soft distillation. Yeah, so soft distillation is where we use the the logits that are computed after the softmax. And then after the hard distillation is where we are using the true labels and the student prediction, but also it's also computed in terms of zeros and ones, whereby the highest probability or the highest probability density becomes the one, and then the others are automatically now or zero down to zero. So 1 minus alpha multiplied by the distillation loss gotten through the teacher and the student predictions. Yeah, so if you go to the cross entropy, it's used to convert the logits into probability density that later turned into the hard for soft distillation. Yes, so the softmax function here, you see, the probability is calculated through getting the exponential of the logit, and then the sum of over the sum of all logits. So it's given as a fraction of all other logits, the exponential of all other logits, the sums of all other logits. Yes. So knowledge distillation, here we're seeing our teacher model teaching the student model, as you see. So it goes on to be trained. Then this compression technique involves a large model, teacher model with high performance transfer weights. Yes, we've looked at that already. So the methodology, segregation transform from process performance over the convolution due to the higher competitive modeling capabilities. In this work, vision transformer input layer had size images resized to that pixels, and then they were split into patches, which is the attention process. Then for the image, that results into 196 patches when you multiply the image and the pixels for the patches. Now, the output layer logits were spread over the 10 classes correlating with the input. Now, each patch was linearly projected into the 768. And then I fed into the MLP, which is the feed forward network. So the model had 6 successful transformer blocks. Now, feed forward network is one of those blocks, and then it has a hidden layer with 124 units. Now, data distribution. We used the CIFAR dataset because it was the low-hanging fruit. It was the available one. My dataset had only one class, which was the TB, Microtuberculosis bacterium, and time was required to probably annotate the others, which I didn't have. So CIFAR dataset has 6,000 images, 5,000 for training, and 1,000 for validation under 10 classes. Now, the summary, as you see here, we have our metrics computed across or against the ResNet, ShuffleNet, AlexNet, MobileNet. So the lowest in accuracy. So as you see here, ShuffleNet gets to have the lowest inference, 0.2, and then it's neighbored by, it has a neighbor here, which is VGGNet, though you see the size of VGGNet is not practically deployable on a machine learning device, but ShuffleNet has a 20.4. The list is of course MobileNet, but it had a very high inference, so it's not practical when it comes to inference time. Now inference time, yes, as you see here, we plotted it, but as I've discussed, ShuffleNet has the lowest inference compared to the rest. Yes, AlexNet also tried to perform having a low inference, but due to its large size, it's also not, it's less advisable than the ShuffleNet. Discussion. The most vital performance metrics in tiny are the inference time, which detects the speed of the application. AlexNet and ShuffleNet reflect registered the performance best values, but ShuffleNet distilled model is 8 times smaller than the fastest AlexNet, which is considerable because model size is also a vital factor in edge devices that have limited storage and compute power. ResNet learns faster from the vision transformer than the rest of the models, but has a significantly longer inference time than the ShuffleNet, which learns way slower. Yeah, because it has a high accurate loss. Yeah, ShuffleNet, but it gets to have the inference. VGG learns second fastest, but has the 25. Yeah, so it has the 500 and something MBs. And ShuffleNet conclusion and further work, its deployment of these machine learning applications prioritizes inference and model times due to the model size, due to limited computation storage and devices and compute power. So this work registers ShuffleNet as the best suited model. That's our conclusion for this lesson with transformer, vision transformer, and teacher as the teacher model. Further research is going to involve evaluation of pruning and quantization methods against the same 5 students' models for comparison and further conclusion. Model compression may come with trade-offs, but which tiny model retains best performance. Anticipated limitation. So edge devices to test the models are costly, but then I have a Raspberry Pis that I can use I'd probably test the models, but I don't know if time will allow for me to work on the installation and deployment. Time constraints to train the various models, GPU constraints to train the models. Yeah, so for the GPUs, I used, I think, like 6 emails to use Colab, but yeah, all the emails did the job. Acknowledgement. I would like to give a vote of thanks to my supervisor, Mr. Gazong Marvin, for his time and patience and guidance invested in his work. Last but not least, my classmates that offer support in all forms and support the common cause. These are the references, but one I really commend is the second one, which is by Hiton, the Nobel Peace Prize winner, and also Busila and Rich Caruana, which Hiton also references when it comes to model compression because they use the ensemble models. Back then, they were one of the pioneers in model compression, and as you see, even the title is model compression, nothing else. Other than that, I beg to submit. Thank you.